Usually these kind of machines, they work similar to the binder jetting, but instead of printing the glue onto the powder, they basically produce thermal energy to melt the powder into the desired pattern. So most machines, they use the laser to melt the polymers or the metal powders so that they can build their three-dimensional objects. Some of them, they use electron beams to melt the metal powders in a certain patterns so that they create their ultimate 3D objects needed. When we are using polymer powders, basically the powder supporting the part, it make it possible to create complex three-dimensional objects without any kind of supports as well. Metal powders, for the metal powders, the thermal shrinkage of metal parts during solidification, they can make some parts to warp or to bend. And so supporting these objects can be done by attaching the part to a thick metal base plate so that you can maintain the accuracy of the part and in the same time restrain from any kind of warping or 3D dimensional defects. So the metal supports are machined off after the part is completed. So usually the powder bed fusion machines are used in the additive manufacturing machines to create end-used parts that can be highly engineered products. So usually this kind of technique is used for engineering application, either if the part is being used in engineering application or for demonstration purposes. So the polymer and the metal parts, they are made using these techniques, and recently they are becoming more widely used in aerospace, defense, and other high-end engineering systems. These two parts are examples of the powder bed fusion. You can see on the right and on the left some thermal fans that are used in some engineering applications using this kind of 3D printing technique. The next technique we are talking about is the directed energy deposition. Usually the machines using the directed energy deposition, they melt the material with a laser or any other energy sources so that the material can be deposited. The art of work for these machines is similar to the material extrusion, but instead of melting the plastic, you are melting the wire powder or the metal powder to be able to flow through the nozzle and eventually deposited on the part. We can see here in the illustration we have the so let's change the marker in here to laser pointer. So we have the electron beam and we have the material or wire supply, and both will intersect on the bed or the build platform. Then you have your object that is created by depositing layer by layer. Another illustration of directed energy deposition. So you have here ceramic powder, we have a powder air jet, then you have your laser being mirrored in the needed pattern, then you have your substrate in here, and this is the part being built by layer accumulation technique. Again, another illustration showing you how the powder is converging with the powder delivery nozzle and combined with the focused laser beam. Then eventually they have a melt pool, whereas the deposited material will be in a liquid state, then solidifies after a while to create the required layer. And here we have the substrate where the layer will be printed. So a 3D illustration of the previous illustration. We have here high energy beam of electrons. Then we have here the power delivery system, and we have the previous metal layers. Then we have the new metal layers being deposited while the nozzle is moving XY directions in the space based on the orders sent by the 3D printer. You can see here, so this is the depositing nozzle. In here you can find the electron beam, and the powder beams are meeting each other in here. Then the deposited material will be placed in here while the nozzle is moving in XY directions in this space. This part is an example of what the direct energy deposition 3D printing parts look like. So it's not the best resolution, but still it is able to produce some usable parts for certain applications of engineering and other life applications. So if you want to make the parts with overhangs, then in the direct energy deposition system, so you need either a 5-axis deposition system so that you can change the material orientation while printing, or you need supported material. So these systems usually used to make metal parts or metal ceramic part composites. So support material that are used need to be machined eventually so that they can be removed. The usage for this kind of 3D printing method is basically to add features to an existing structure. So in this case, adding or strengthening grips into a plate, for example, or you can use it to repair a damage of a worn part. And some cases these processes are used to build a whole metal structure. So they are called as a metal deposition additive manufacturing machines, because basically they deposit metals or metal ceramic mixes for certain applications. Regarding the sheet lamination methodology, this technique basically cut and stack sheets of material on each other, as we discussed before. This approach can use papers, plastics, and metal sheets so that it will build up a wood-like, plastic-like, or metal-like parts as needed. We can see here a 3D illustration of the sheet lamination. So you have the hot plate up here. You have the adhesive nozzle in here. Then you have the platform being raised up or down, and you have the base moving right or left, and the nozzle itself is moving in the axial and lateral direction. Then you have here the paper feed mechanism where these papers comes in, then you cut the layer needed and you do some adhesion, then you create a new layer as well, and so on until you create your 3D object. Sometimes you combine a couple or triple of additive manufacturing techniques so that you can create a certain specialized 3D object. This method is called a hybrid and direct write additive manufacturing. So basically, additive manufacturing is combined with subtractive techniques, so that such as the computer numerical control milling or the laser cutting. When you combine like a simple horizontal milling head into a material jetting machine, so the solid scape create a popular line of high precision wax printing, and this layer thickness can be up to 0.005 inches, and it is heavily used in jewelry industry so that it can create wax patterns for custom jewelries. There's a couple of additive manufacturing techniques that have been modified so that they will work for the small scale and deposit passive electron structure, same as conductors, insulators, resistors, etc. These techniques known as direct write techniques, and for example, they use electronic inks that contain nanoparticles, they will give for their print and electronic properties after drying, or even thermal decomposition or post-treatment. So some applications, they use electronic inks, they contain nanoparticles, they give the printed layer electronic properties after they've been dried and thermal decomposited and been exposed to a couple of post-treatment applications. If you combine the direct wire technique with the other additive manufacturing techniques, so it gives you possibility to create multifunctional 3D embedded electronic structures, so on a basis of layer by layer. So you combine the structural, thermal, electronic, and other functions into a single component, which can give more advantages for this kind of hybrid processes. The impact of additive manufacturing on the manufacturing sector. We can see here these kind of surveys based on a survey of 2017. We can see additive manufacturing is used 16% in medical or dental, 21% in consumer products or electronics, 13% in industrial business and machines, 10% in aerospace, 18% in automotive industry, 4% in architecture, 6% government or military, and 8% in academic institutions for teaching purposes, and 4% others. So you can see there's a significant impact of additive manufacturing on the manufacturing design. And in that case, as example, the rapid prototyping techniques are evolved. So you can now create three-dimensional objects directly from a CAD data. So it will allow the designer to print a 3D representation of the design and being able to do functional testing during the design process. As well, the additive manufacturing, it gives you a shorter time to get hands on your prototype for the new design, which allows us as engineers to do more optimizations for the design and propagate through manufacturing, which will help you catching any errors or flaws before you do the mass production for that part or assembly or product, and will be a kind of costly mistake if you find any. The top 3D printing technologies used, you can see 2016 and 2017 surveys. Let's use 17. So for the FDM, this kind of printing technique is used 36%, and selective laser sintering 33%, SLA 25%, polyjet 13%, digital light processing 7%, direct metal laser sintering 8%, selective deposition lamination 2%, binder jetting 4%, electron beam melting 2%, laminated object manufacturing 1%, selective laser melting 4%, and the CLIP 4%, fusion jet 2%. So in this way we can see the FDM still the most used technique for 3D printing so far in an averaged values for all industries. So the layer by layer approach for additive manufacturing is suited for highly complex geometries, even geometries with internal gateways and undercuts, and even the features that are difficult or impossible to make, they are able to be done during the layer by layer approach of additive manufacturing. If you have small, highly complex objects, additive manufacturing powder bed fusion processes, they are sometimes cheaper than the injection molding if you are planning to do big volumes of products like 100,000 components and up. Uh, However, the larger the part or the simpler its geometry, the more cost-effective traditional manufacturing processes become compared to the regular additive manufacturing processes. We can see here the global 3D printing market forecast for 2017 up to 2025, with 2017 dark blue, 2026 in red. We can see here electronics and consumer products are going to increase more as moving toward the future. For healthcare applications as well, automotive and aerospace will be doubled. For construction, so it's almost doubled everywhere. The market share by technology, basically polyjet number 1, stereolithography number 2, FDM number 3, EBM number 4, SLS number 5. We can see here based on the map that East Asia Pacific is the fastest growing region, and North America is the dominating region in 2016. So North America is now dominating, Asia is coming on the way. So the additive manufacturing is suited for, as we said, for parts with complex geometry that are made low volumes for personal customized uses. Now today the additive manufacturing is used in aerospace systems, where you can even find it in space stations, micro satellites, F-18 fighter jets, even Boeing 787 aircrafts, and more. For custom dental aligners and hearing aids as well. Additive manufacturing techniques, they're commonly used as assembly jigs and fixture by BMW and other automotive manufacturers for more ergonomic, accurate, and quick assembly for automobiles. We can see even NASA started to create some 3D printed product and 3D printing printers and send it to the space in case the astronauts need some kind of tool that they don't have, so you can save a lot of money. Instead of waiting until you get the tool from Earth, then you can just make it on the go and start using it. As we can see here, some of the customized 3D printed products for automotive applications. The key benefits for additive manufacturing techniques that you don't need tooling or specialized hardware for any individual component. Each part have his own unique part created just before or after it. So the manufacturer who distribute the additive manufacturing machines close to the assembly point, or even at the end to the end consumer, it's basically changing the logistics and distribution models for manufacturing rather than concentrating manufacturing where tooling is located. Additive manufacturing as well involves human involvement to create parts. So it's not only an incentive to offshore manufacturing to a region of low-cost labor. So onshoring is standard for additive manufacturing as well. The good opportunity for additive manufacturing technique is in the area of spare parts production as well. Auto production components can be replicated using the 3D printing. Scanning techniques can easily capture the geometry of a broken or old part, so you can redo it or replicate it using 3D printing and through the CAD generation design. So people these days who try to restore the old automobiles or aircrafts, defense systems, other machines that are designed and built long time ago. So there's no CAD drawings, there's no reference sketches for these kind of components or machines, so you can just redo it using the 3D manufacturing as needed. For the consumer personalized manufacturing, additive manufacturing is starting to move to the mainframe manufacturing arena. It's moving from the mainframe to the personal manufacturing arena. 2010, there is 5,978 personal machines sold. All these machines are material extrusion machines. Most of them are sold between $700 and $1,500, and you have 6,164 from the other additive manufacturing systems and techniques. 2007, the additive manufacturing machines first became available, and 66 personal additive manufacturing machines were sold compared to 4,938 other additive manufacturing systems. So the main frame of additive manufacturing is growing with a respectable rate, but the personal additive manufacturing market is growing dramatically. So with economic background, the personal AM machines, they are sold at cost of 0.1 up to 10% of the cost of other additive manufacturing machines, and personal market is still small, but it's growing, and this growth is going with the high curves, and it's just the future is promising. More and more consumers will enter this kind of will enter this technology to their homes and being able to do all kinds of products using that. So if you compare the 3D printing and the 2D printing, basically for 2D printing, there is a stable mix of high volume printers for newspapers, magazine, advertisement. Then you have medium volume printers like digital photocopiers, or low volume printers like laser and inkjet printers. But the same way, a consumer can purchase a mass produced poster, print their own photos, and use their own inkjet printers at home. 3D printing is most likely it will be used by major manufacturers in factories and local suppliers in neighborhood, so that, and even within people homes in the near future. In a similar manner, the consumer can purchase mass-produced posters, print their own photo at any kind of local store. They use their own inkjet at home. 3D printing will be the same thing. There will be outsourcing manufacturers everywhere. They are competing with their prices. It will be a good price for everybody, that you can just order as much as you can of 3D printed parts of your own design, or even you can have it at home and print as you need it.